i chciałem zaprosić naszego gościa, Daniela Siraguzo, który jest przedstawicielem niemieckiej firmy postprodukcyjnej, która będzie robiła, już przedstawi się zresztą, ale dla tych z Was, którzy nie byli na poprzednim wykładzie, robili całą obsługę produkcyjną, że mają wspaniałe urządzenia, będzie o tym pewnie jutro mówił, mają taki karawan z przenośnym kinem 3D z możliwością wszelkich korekcji, łącznie z barwnymi i ustawieniem 3D, konwergencji. Także przyjemność pracy, bo po zdjęciach od razu się oglądało na dużym ekranie materiały z planu zdjęciowego. No i zapraszam go tutaj na wykład ostatni. Wiem, że dzisiaj mieliśmy maraton, ale to wina jest troszeczkę leży po stronie kolegów CG Projekt, bo oni mieli być wczoraj, no i w związku z tym nam się dzisiaj tak skomasowało, że mamy taką straszną ilość wykładów w ciągu jednego dnia. Welcome, Daniele.
Okay, thank you very much. I haven't understood a single word, but I hope this were a nice word. So, okay, thank you, thanks, Slavomir. So my name is Daniele Siragusano, and today, so I'm a post-production stereographer, normally doing all stuff related to stereoscopic imagery and what's happening in post-production. But today I will focus on the fundamentals of depth perception. So how do we perceive depth? Because we have to know how we are perceiving depth to make the right decisions on set and in post-production. But this is the most important slide I've ever done is this, because when you're shooting no problems. This is actually a good example for this slide, because we see that we have now a little bit of a vertical parallax here, but this is exactly what this slide is telling. So if you're shooting a stereoscopic movie, you have to be aware that the whole chain from the geometric relation on set, so the staging of objects between each other and the camera, so the whole production, how the rig is set up, the whole post-production process, and the screening to the geometric situation when you watch the content, this chain has to be keep in mind to estimate the right depth perception. How do we perceive this scene? So we really have to take this into account. And for now, if we would now watch a stereoscopic movie and we would have done the scene perfect in the production and the post-production, but the screening goes wrong, then the whole chain is broken. So you have to take care that every part of the production is made in a high quality to guarantee a high stereoscopic image on a high level. And we will concentrate now on the last bit of the whole chain, which is how do we perceive that? So I just move on, because now we don't need the stereo projection for the first bit of the part, because we're concentrating on the depth cues, which you see with one eye. And these depth cues are available in still photography, in moving picture photography for 150 years. So we call them also pictorial cues. And then in addition to the pictorial cues, we got cues that come from having two eyes, and they call it binocular depth cues. So I probably, you heard all about the monocular depth cues. I will just really quickly go through them. Oh, this is nearly okay. One pretty strong depth cue is relative size. So our brain calculates from objects where it knows the real size. This is no 3D slide, so you don't need the glasses. I tell you when you need the glasses. Because we are at monocular depth cue, so there's no need for the glasses. For objects we know, we estimate depths by the scaling of the retinal image. So objects that are farther apart will be projected smaller on the retinal image, and objects that are bigger will be projected bigger on the, which are closer will be projected bigger on the retinal image. And from this cue, relative size, we estimate depth. So we know that this one is not a miniature of the other guy, but he's standing behind it. Another really strong monocular depth cue is perspective, which actually is derivated from relative size, because you're having the same actual size, but the further apart this road goes, the smaller it gets. And if you have objects that are going through space, you get this, what we call perspective. So perspective is a really strong one. Even more stronger is occlusion. We calculate or we estimate depths by the information of occlusion. So we know that this tree is in front of the house because it occludes the house, and this tree is behind the house because it is occluded by the house. So this is extremely important when you're working with stereoscopic image and you're putting graphics and titles on to get it right. So we will come to that later. One weak depth cue for near distance, but really strong depth cue for objects that are really far apart is atmospheric haze. So the atmospheric haze will reduce the contrast for objects that are really far apart. So like the mountains in the background, they are washed out in terms of contrast, and they are, because the atmospheric sky is blue, they are, from color, in terms of color, they are pushed to blue. This you also have to take into account when you're doing color correction, that you can use color coding as depth cues. Another thing is textual gradient and light and shadows. Our brain is really good in estimating depths from light and shadows. So we know if here is a bulb and we got shadows here and there, that this object must be behind the light bulb and this in front of the light bulb. Especially with faces and all that kind of things, our brain is really trained in getting depth cues out of light and shadows. And there are many more, but the last one I will mention here is motion parallax. We all notice when we're driving in a car, we're watching outside the window that objects that are closer to us will seem to move faster in front of us than objects that are farther apart. This is basically because a point here, which moves the same speed as this one, needs shorter time to get the same visual angle than this one. And this is also a really strong cue, which is not usable for still photography, but we can have this depth cue for motion picture, where we have motion parallax. So the sum is the perceived depths, and this is not only true for monocular depth cue, but for all depth cues, is the sum of all depth cues. So the brain does not only generate single depth cues, but it adds them all together. And the more depth cues you have, the stronger your depth perception will be. It is a cognitive process, so you need semantic analysis. So you have to figure out that this amount of pixel is a face, and this amount of pixel is a face, and the face is smaller. So it's not a neuronal process, the monocular depth cues, but it's a semantic analysis. You need object recognition, and therefore it's on a high complexity level. And later we will hear something about Gestalt theory, where this comes into approach. This is a good example where you mix up different depth cues, and you can also make them dissonant to each other. So probably all of you know this so-called Ames room, where the room is really distorted, that when you're watching it from a certain perspective, it seems to be, in terms of perspective, straight, but in reality the room is really distorted. And so you can also see that some depth cues are stronger than others. So we don't perceive a room that is distorted, but we perceive that the one woman here is smaller than the other. So perspective in this case is stronger than relative size. Any questions about monocular depth cues, or should we take the questions at the end? I think it's better.
Normally we are doing.
Yeah, okay. Now, this was just a brief introduction to monocular depth cues. Now we're adding the third dimension, or the third eye, because we already heard that also with one camera we work in 3 dimensions. We add now with stereoscopic filmmaking binocular depth cues. And there are a lot of more binocular depth cues than on this slide, but these are the strongest one I want to focus on. First of all, stereopsis. Stereopsis is actually the sense of 3D, the sense of the perception. Then one really, really strong depth cue for our brain, which is mostly not known in the motion picture industry, and that's why I'm always mentioning it. It's binocular occlusion. And then we have a brief look about what the Virgin's position of our eyes tells us in terms of stereoscopic depth perception. So stereopsis 101. This is the most benefit of having 2 eyes. We're having always a fixation point F here where we look at, and then we have other points in space. And if we see here, we should align them a little bit better, the slides, the projector. And you see that these points A and B fall on different places on the retinal image. So the left eye view sees this, and the right eye view, oh, this is a little bit rolled in. Okay, but you see that the blue lines are contrary to each other, and the red line as well. So we got disparity here. So disparity is the difference. We see that, the retinal images are different to each other. So, and this retinal disparity elicits stereopsis. What we also can see about this is that for really getting stereopsis, we need at least 2 points, because stereopsis is just a relative sense, no absolute sense. So it's always comparing other objects to the fixation point.
I'm sorry.
Yeah.
Actually, if you put your 3D glasses on, you can see it very well.
Yeah. So actually, if you put your glasses on and you get, actually you wouldn't get disparity, because each plane is moving at the same distance. For disparity, you would need different distances and different objects there. So, that's good. This is basically the same. I will shortly, just to make some terms right, onto the screen, when we're talking about disparity on the screen, we call it geometric disparity or relative parallax at the cinema screen. This is extrinsic, so this happens outside our world, outside our eyes. And this geometric disparity causes retinal disparity, or you also sometimes hear about binocular disparity, and this is intrinsic in the eye. You should, when you talk about 3D, you should distinguish between the intrinsic and the extrinsic meaning. The relative parallax, this is a term for you, I quickly describe it. For example, if you have an object which is on screen plane, then his absolute parallax of this one point is 0, because the horizontal offset is 0. So it will be perceived, if you watch it, you will see no double images there. Then if a point behind it, this maybe have a positive parallax of, let's say, 20 pixel. And this is the absolute parallax of this special object. And when you're talking about relative parallax, you're saying the distance between those. So in our case, it would be also 20 pixel relative parallax. Another case, for example, if an object is in front of the screen and it has an absolute parallax of -5, and another object is behind the screen at 20 pixel, we got a relative parallax of 25. So you're always saying the depth budget or the relative parallax. And this is important because this elicits stereopsis. And to get a better understanding about the stereopsis, I show you the limits in terms of how accurate it can be, how far you perceive, how far distance can be perceived in stereopsis, and where are the limits. So we start with the stereoacuity. So how fine is the sense of depth perception? The minimal critical angle, it's measured and it depends on lightness and sharpness and physical condition, is about 2.5 to 10 second of arc. So second of arc is a measurement of angle, because when you're talking about disparity, you always, you're not measuring centimeters in the real world, you're measuring always angles on the retina. So you won't see, if I'm talking about disparity, you won't see any metric units, because it's only angles, and this is pretty important. So it's about 2.5 to 10 second of arc, and therefore it is smaller than the spatial resolution of one eye, because the spatial resolution of one eye is about 1 minute of arc, and not 5 to 10 second of arc. So we can calculate small differences that are smaller than the resolution of one eye. I give you a quick example for those of you who are not comfortable with angles. If you have, for example, an object which is 40 centimeters away from you, let's say like this, and the second object is 40 centimeter and 1 millimeter, is this a lot stereopsis for our brain or not so much? So I've done the math here, and it's 82.5 second of arc. And if you see the threshold is between 2.5 and 10, 82.5 second of arc is a lot of stereopsis. So this tiny difference in space will give us a lot of stereopsis. So actually the threshold for 40 centimeters is 0.12 millimeter. So we are really, really accurate with stereopsis. You have to keep this in mind when you're building up your sets, that you can really see tiny differences. On the other hand, can we see with our two eyes that the moon is closer to us than the sun? Question mark. This is pretty simple to calculate. You just say, when you're looking to infinity, to the sky, your eyes look parallel. And as we know the stereoacuity, we can pretty simple calculate for an object with, compared to the infinity, have an angle of the stereoacuity. For all of you who don't want to do the maths, I've done it for you. Depending on where you put your threshold, if you put the threshold really high, you can say 6.6 kilometers. So in words, it's saying a mountain that is 6.6 kilometers away can be distinguished between, let's say, the moon or the sun. So so the stereopsis really lasts really long. For us, with 2K cameras, this is pretty important, because this is what actually our cameras can result. And for 60 second of arc width would be the stereoacuity for a 2K camera. It's still 220 meters. So you get the range of really fine really fine disparity in the beginning, up to several hundred meters away. But of course, the most stereo is perceived in the first 10, 20 meters. Then it gets really less and less. What are the limits? Can we see the difference of 40 centimeter to 40.1, and at the same time the 200 meter, the object which is 200 meter away against the sky? Can we perceive this at the same time? No, we cannot. We have a really small area where we really perceive single vision, where we really see the images sharp and as one image. This is so-called Panum's area. And here we really see one object, so we don't see double objects. In the area between the Panum's area and this red line here, we got the amount, the depth budget we can work with. And after this line here, the images get too different to each other, so that we cannot fuse them anymore. And what we call it in visual science, this kind of viewing, we call it diplopia, or Latin stereopsis. In this term, you cannot really distinguish anymore if objects are behind each other or not, so you got no quantitative stereopsis, but only qualitative stereopsis. What does this mean for us when we're doing movies? Here's Panum's limit. So first describe this X. This is actual binocular disparity in minutes of arc. So for you to imagine, as this line goes here, your objects, your relative distance go bigger, bigger, and bigger, and this is the perceived size, which we really perceive as depth. And as we can see, it starts here where the stereo acuity is, and it's pretty a straight line. So the more depth you give the scene, the more space perception or depth perception you get, the more perceived depth. But then we come to Panum's limit here, and then it gets a little bit less until there is a maximum depth. And if you then furthermore increase your depth budget, you will get into what we call diplopic imagery, and then the perceived depths will fall off. And what you, as a stereographer, have to figure out is where is this point and how do I reach it, and when do I stop adding more stereo. There is a blue, a green, and a red box here. Okay, the red box we should avoid, but what is the green and the blue one? So the green one is what we actually have for a 2K image available, because the stereo acuity for a camera rig ends up here. And this blue line is not yet used with 2K imagery. So if we move to 4K or even 8K, we can use this low end here. But now in the days of today, we're having only this bit where we can play with. Vertical disparity. Vertical disparity can be easily achieved when you're doing misaligned camera rigs and all that stuff. So you force your eyes to that one eye looks down and the other one looks up. But this also happened in a small extent in the real world. Always when one object is closer to one eye than the other, then the retinal image on the object that is closer is bigger, and then on the other one is smaller. So you have vertical disparity in real life, but it's normally in a really less amount compared to horizontal disparity. So for stereoscopic movies, you should mostly avoid vertical disparities. So let's talk a little bit about fusion and how we could use this also when we make decisions for editing, for example. The fusion is the process when you combine both images to one image. Maybe you have asked yourself, well, I have two eyes, but I don't perceive two images. I perceive one image, like the Cyclops in the first slide. We have one eye in mind, which is the cyclopean eye, and there's also a whole visual scientist, visual science that are just, they call it cyclopean depth perception, and it's about how we fuse it. And from this we know that stereopsis is a parallel process. So it's not starting at the one line and then scanning all the area. We have a lot of neurons in our brain, and they are doing the fusion process at the same time. So normally you don't have really long time to fuse an image if it's a good image, because it's a parallel process. So it does not matter if it's SD, HD, wide angle or not. Stereo fusion is an instant. We have two kinds of fusion. We have global fusion and local fusion. The global fusion has only two states, fused and unfused. And this means you look at the picture and it's fused or not. But there can be local parts in a global fused image which are not fused. So there can be artifacts where when you look there, you have no fusion there, while having the global fusion still activate. So yeah, you have to take this into account, especially if you're dealing with artifacts and all that stuff, that you can achieve a global fusion without, with some local parts that are not fused. The fusion fusion is a complete neuronal process, so it's going faster than our cognitive processes of object recognition. So until I have recognized that this amount of pixel is a face, and this face, let's say, is John Travolta, I have to go to my memory and recognize this kind of pixels with John Travolta, and this takes much longer than the fusion time. So the fusion time is masked by cognitive process. But if the quality of the images are not good, the fusion process takes longer. So the fusion time is 1 divided by quality. The better the quality, the quicker is the fusion time. And when you're doing a lot stereo and you really get used to stereo, the fusion is affected by practice. So if you like me doing 8 hours a day, you watch stereoscopic images, you can easily fuse images that are completely unaligned, because this is a practical process. And you have to keep this in mind, that things that you can fuse if you're a professional, other people may not can fuse, because they're not practiced like you. It's always good to know what happens before stereopsis and what happens afterwards, to maybe with this knowledge you can gain stereopsis in certain parts, and in other parts you may reduce the effect of stereopsis. And therefore I tell you what is before and after stereopsis. Before stereopsis we have kind of only pretty low level analytic information processes. The one is a frequency analysis, like a Fourier analysis, and this is basically, we measure the high frequencies in the retinal images. This means basically structure, details and structure. So where you have details and structure, fine details, there you have a lot of high frequent energy, we call it, and this gains the fusion process. And we have a pretty good edge detection on neuronal level. So if you get edges, the edges will help you to get the fusion quicker. So we only use these two informations for the fusion process. So high frequency in the spatial domain and the edge detection. After stereopsis, all cognitive processes take place. All the monocular depth cues, for example, take place after stereopsis. And motion perception. We perceive motion after stereoscopic perception. So, summary for stereopsis. It's our special sense of the depth perception. It is not absolute, so you cannot say if the eyes are parallel, you will perceive infinity, because it's only a relative sense. You need at least 2 objects. So if you have one text and you just put it in front of the screen, you won't get any depth perception out of it, because you need a second image to compare it. The stereo acuity, as I told, is really, really fine, and we can also really, really see in the long distance. And the limits until we get in this diplopic area where we don't see clearly single vision is between 10 and 25 minutes of arc. So we come to the second depth cue, which is really, really strong, and this is binocular occlusion. This is an example here. Always, if you have 2 objects in a scene, you got areas where one eye does not see the area. So for example, this area here is not seen by this eye because it's occluded by this, what we call occluder. The same at the other side. So you have parts of the image which only lives in one eye. So there is no neighbor in the other eye. And as you increase the distance between the objects, these occluded areas get bigger. The same if you increase the interocular, or when we're shooting with cameras, the interaxial distance, also these areas get bigger. And the brain uses this kind of monocular areas to estimate depth. The next is a stereoscopic example, so maybe we get the stereo projection right in the next minute. And I show you an image on the left. This is a simple image just to concentrate on monocular depth Q. I show you an image with no disparity in it. Just you will see. Oh, this was pretty good. Or no, I think one is a little bit. So we give Lucas another minute. Just show you what I will show you. I will just show you two images with no disparity and therefore no stereopsis in it. The only difference is that you have some small angles in the one eye and then in the other eye here. So we have only parts that lives only in one eye, so just monocular occlusion, and then you will perceive depths, hopefully. And what I then do is I just flip them and you will perceive a completely different object. Can you all see this letter C that points towards you?
Mm-hmm.
So this depth perception is only produced by monocular information. And if I switch it the other way around, you should see a C that goes in the other direction, just by switching the eyes. And this should show you that only with monocular information you can produce depth perception. These monocular areas plus the stereo, so because in normal vision, normal stereo filmmaking, we always have the mix together. And they should also be always in a truthful relation to each other to make a truthful depth perception. You can see Clash of the Titans, for example, what was a converted movie, what was not converted very well, because they don't use these monocular occlusions. They just warped the picture with warping techniques and they produced disparity, but there was no monocular areas that were truthfully in correlation with the stereopsis, and that's why a really, really strong depth Q is missing. You got an idea of stereo, but it's not like real live footage. I've got another example here. This is a so-called random dot stereogram, and you should perceive on the upper one that the white area is at the background level. So you got a area here which is in front of the screen, and this white area here is floating just here behind. On this part here, I only added only in one eye, a random dot area. So actually we are telling that there is information for one eye, and we should perceive that now the white area is at the level of the nearer plane, like on this plane. And this is just changing the depth perception just by adding monocular depth cues. Are you getting it? Mm-hmm. So I should have grab a glass as well. So this was binocular occlusion. Really, really important. So always if you have two objects and they're occluding each other, you see with one camera more from the background than with the other. And this is important. And you can play also with this if you want. In storytelling, maybe you see the scissor of the murderer only in one eye. Could be like you're using this kind for storytelling, for example. You could do a lot of things with that. Now we have a brief look to vergence. To vergence position. Vergence is actually how the eyes are rolled in or rolled out. The position, then we look at vergence motion, well, because we're working in a motion picture, and then we look briefly at divergence when we look outside. So we basically diverge. The vergence position, so like how the position of the eyes is, it is a depth cue. So we take the muscle effort for the vergence. This muscle effort, we calculate depth from that. It is mainly important for the direction perception. In theoretical cinema movies where the eyes are nearly always parallel, this is a pretty weak cue, but it is stronger for closer objects like television or even smaller screens. So if you judge a stereoscopic picture on a monitor on set, be aware that the scaling of the image can be affected by your vergence position. For example, I show you here two examples. Here a fixation point F and another point A, and fixation point F and another point B. And you see in real world coordinates in meters, this distance is huge, this distance is small, but the rational disparity, intrinsic, just the stereopsis is the same. So this angle is the same. And that's why, this is one reason why TV and cinema scale so differently. So have this in mind that the vergence position is a weak cue, but it changes when you change your viewing conditions.
Television is left, yes?
Sorry?
Television was left one.
The what?
Television.
Yeah, this was the where you. Yeah, television was where your fixation point is
Yes, but
most of the time.
The
yeah.
left one.
Yeah, yeah.
Oh, okay.
Vergence motion, because we're working with motion pictures and also with still photography. This is quite important. When you watch a normal 2D image and you look around in the picture, your eyes are always moving parallel, so they don't change vergence position because you are just looking around in a plain image. The eyes move parallel. In a stereo image, when you look from one corner to the other, the eyes make a vergence motion depending on the content. The vergence motion is a secondary cue. So if you look in the distance, then the brain expects that you also have to do a conjugated vergence movement, but it's a secondary depth cue. But there can be also dissonant vergence movements, and this can disturb the final depth perception. For example, in America, they have this kind of convergence pulling style when, for example, an object or a person is coming towards the camera, they change the angulation of the cameras to keep him always the same, so he will always perceived on the screen plane. But if we consider vergence movement, our eyes would expect that if it comes closer to us in depth, we expect a corresponding vergence movement. If we cancel that out in the camera, or also in post we can do this, then we got a dissonant depth cues. This stereopsis is telling it comes closer. Also the retinal image is getting bigger, but the corresponding vergence movement is missing. So you can see this on all Cameron productions, that when people come closer to you, you get the thinking that they grow a little bit because they're coming towards you and they're getting bigger, but they stay on the screen plane. So keep this in mind when you're composing shots in the scene or also in post-production, that the vergence movement is a secondary depth cue, but it is a depth cue. Now, when you work with big screens, you can easily achieve divergence. You can easily achieve absolute parallaxes that are bigger than your interocular distance, and people are afraid that if you have more than 6.5 centimeters parallax on the screen, that you suddenly will get headache. Divergence again is nothing you should measure with a ruler on the screen, because like everything in the eye, it's an angular relationship, and it has nothing to do with the measurement on the screen size. And Dr. Salomon is a well-known optometrist, and I have asked him what would be the tolerable divergence, and he asked that the tolerable divergence is about 4 degrees, but since this is a maximum value, it might fatigue the eyes, and so a value of 2 degrees is a more comfortable one. And for the most people I know and I work with, they are having even a more harder constraint, is saying about 1 degree of divergence. This has nothing to do with 1% of budget or something like this. This is just degrees in the eye, and you have to calculate by your own how much pixel this will mean for each screen size, or you can ask me afterwards.
it depends on where the spectators
Exactly.
sit? Yeah.
Yeah, exactly. This is a really good point, and I had a
the farther you sit,
the
better.
relaxer it is exactly. I have a blog in the internet where I have published a SEMTI paper. I had 2010 in New York. I had a presentation exactly about divergence and what is the master screen size. And if you're interested in this kind of area, you can visit my blog. I have posted everything there, and to get deeper information about this. So, but again, you cannot really say about it's 1 degree or 2 degree or 4 degree. It depends on each person, and it also depends on the image layout. For example, if you have a perspective and your eyes watch the perspective and they were slowly introduced into divergence, they can really have way more divergence and it will be comfortable compared to if you have one object standing in front of the sky or in front of a mountain and you watch the person and then you watch the mountain and you got a really abrupt divergence. So it again depends on the layout of the image. So you cannot say you have a sum of rule, but then for each picture you are composing, you have to think about these image layouts and how divergence may affect your picture or not. You can say that, for example, if you hold one hand to one eye here, you get immediately what we call a growth suppression. The whole image of one eye is suppressed. In our case, it would be the eye who sees the black image. If you put one eye close, you don't see a black image, you see the other eye. This is a really extreme case of suppression, but this is how it works. So the brain picks the one where it gets more meaningful information out of it. But there can also be example where the suppression changes over time. And for that we got another stereoscopic example. This is the word for Lukas to put. And sorry that maybe for some of you this will hurt, but I have to do this. and if you watch this, you get the idea of the suppression. You can really, if you go into your head and see what is happening, your brain tries to give the superior to one eye, and then it changes, and you get really this confusion and the conflict in your brain. And this is what we call suppression. This can happen if we're having too much disparity, extrinsic speaking, in our image. We get too much confusion, and then a fight in our brain starts. This is called rivalry. Just keep it. I give you some of these. Rivalry and suppression are correlated. Rivalry is the fight, one eye to the other, and suppression is when one eye has won. Yeah? And in normal viewing, we're not aware of suppression, but it happens all the time. When we are laying down on a carpet, on a pillow, the one eye don't see anything meaningful, but the other eye sees the TV set, and we're basically watching 2D. And because the one eye is completely suppressed, in normal vision we are not aware of that. But in 3D cinema, if we're producing this kind of suppression, it may cause this what we call fatigue. And also this suppression and this rivalry is a thing of practice for a lot of people. And when they work really long with stereo, they know the suppression and it does not harm anymore. But for people who are not experienced, this suppression will really confuse them. And we have to do a lot of more research in this area, why in normal vision suppression is no problem for us, but in stereoscopic cinema it is a problem. Which eye wins the rivalry? Which eye loses? Again, the answer is in the layout of each individual image. This example here is a contour example. So we're on one eye I present you just a blank yellow image, and on the other one an object with contour, and we see that something, if you have a contour in there, it will win against the other eye. So again, high frequency, edge detection, all this neuronal process also are part of this suppression and rivalry. Similarity. Sometimes I give you this one. The combination, the final perceived image is a combination of both. Maybe you perceive a X and you take parts of the one eye and parts of the other eye. And this can also happen if the two are equivalent to each other. Yeah, so this can also be that you use parts of this eye and parts of the other eye. Stereoscopic cluster. I told you about surface perception, that we perceive the material, the haptic of objects by small differences in the shading. This is a pretty extreme case of difference because one is black with white lines and the other is white with black lines. But you see that you get a feeling of a metallic surface because in real world, metallic is different in one eye to the other. So we call this so-called stereoscopic cluster. And the last example, and then I don't hurt your eyes anymore, is the color. And this is especially interesting for color grading because if you have two different colors, and this happens when you work with a mirror rig, you get polarization, you get different camera settings. We will hear about this tomorrow really in detail. And you will see that the perceived color is a mixture of both, and it can vary over time. So maybe you see now at the one time you see a green picture, and the other then you see a red one, and this can change over time. So this is pretty important that when you're doing color correction, that both images are really good match to each other, that you don't get this kind of ambiguous color perception. Yeah, when does binocular rathery and suppression start? Well, I've told you this before. It's in this kind of area when the two images are, when the retinal disparity is too big, or when the two images are too unequal. If the images that you present the eyes are so unequal to each other, then you get these confusions. And the visual system, in the extreme case, cannot fuse them anymore, or can locally not fuse them anymore. Also, we know that, do I have it in the next slide? No, but I can tell it. Also, when you're getting more depth contrast, more volume in the scene, the monocular areas only seen by one eye are getting bigger. And this also adds the effect of rathery, because small areas of monocular areas, we use them for depth perception, but if they are getting too big, if I'm having really strong interaction distance, then I have really big parts in the picture which are only seen by one camera. And if their parts are getting too big, it's also disturbing and causing rathery because you cannot match them to each other. For motion graphics in stereo 3D, if you add layer onto motion or you add subtitle, this is also a really common depth rathery. We call it depth rathery. For example, if you have someone in the foreground and you're putting, let's say, a graphic over him, let's say a title or something, you have to make aware that this title is in front of him in terms of absolute parallax. Because if it would be behind him, in this area, locally, we would have a depth rathery because the monocular depth occlusion is telling that the titles are in front of the object because the titles are occluding it, like my hand is occluding my stomach here. But another depth cue, for example, disparity is telling that my hand, for example, or the subtitle is behind him. And so we get depth ratheries. We also get this on edges when we have objects in the foreground which are cutted by the edge screen. This is by the edge of the screen. This is exactly the same. The object is occluded by the screen, so one depth information saying it must be behind the screen because the screen occludes him. Disparity is saying that it's in front of the screen, so we get a conflict, a rathery there. Yeah, I think I have said that everything. It's affected by the layout of the image, and generally speaking, you can say that brighter suppress darker ones, images. High contrast suppresses low contrast. Sharpness wins over unsharpness. And foveal parts, so parts in the middle of the fovea around the fixation point, win against peripheral vision. But for the most time of a stereoscopic image, stereoscopic movie, we should avoid these strong rivalries. We should stay in the safe zone, and we can, if it's motivated by the story, we can produce rivalry if it's correlated to the story, of course, and you can go over the limits for a shot or something like this. This is no problem, but you have to be aware that there are certain limits. So I have to. Have you any questions? Because I have a quick drink here.
I have a question about suppression and rivalry. Does the outcome come after a specific period of time, or is it automatic? Because when I was looking at the vertical and horizontal line, I could literally see the battle
So
going on. And would it have, if I continued to look at it, would one have one eye won over the other?
In this special case, not, because they were so equal that you would fight.
It would constantly
fight.
Okay.
Yeah, but this against
nothing would happen over the course of time.
Yeah, I'm not pretty sure. I've written that we have to do more research in this area. We know that there are suppressions, but it's really complex because there are different kinds of suppressions. Suppression and rivalries affected by color, affected by contour, and there has to be done more research if how this will be affected. We have some research in the visual domain with like people and vision science, but not in terms of stereo cinema, how suppression is perceived in stereoscopic cinema. And there's a lot of research going on at the time.
Because also you mentioned that the longer you stare at an image, like you were saying yourself, where you work 8 hours a day, and it begins you almost automatically put the image together. Does that technically mean that the more experience you get, the worse you get?
And no, actually, the better I get. So how do you define worse?
Exactly. Well, I'm saying in the sense of if you put these things together and the audience does not have as much practice as you, and we do not, how can you see what we're going to see?
Yeah, this is exactly what I was mentioning. You have to pay attention when you are practice. So if something is hurting my eye, it's way too much.
Okay.
So I have always to drive myself like to 50%. I would have a little bit more, but I have to tell myself every time. I cannot satisfy myself. Because the audience has not the same practice as I have. So I'm always a little bit unsatisfied, but then I know it's a good stereoscopic image for the rest of the world.
Audience lagging behind, but no, it's a dynamic process.
You're right.
I'm watching my mom.
More and more, perfect.
Something which was uncomfortable,
10 years ago will be, or
after
something.
watching 7 movies, change.
That's
one more question, because it's always this issue, of the subtitles. Is any existing philosophy how to put them, dynamic, we understand, but in front of the characters, very much in front of the characters. What happens if we are in negative parallax? To keep the subtitles even, in this uncomfortable zone, what we are doing, having, let's say, we're having our object, or actor, or whatever it is, is very close to, in the theater, in front of us. Where to put the subtitles? It will be really painful for the audience.
Technicolor has tried to develop an automated process by calculating disparity estimation and doing visual science. And I've seen some of these test things, and I think Tangent, they have a Blu-ray out with subtitles where they use this automated, animated stuff. But it works for a lot of shots, but for the most shots, well, it's not really good. When we do subtitle, we design them, so we put them manually. So this is an additional task, and for the most time, your stereoscopic image or the depth budget in the stereoscopic image goes to the limits. So you cannot, if you put the subtitle, you cannot put it much in front of the first object, because then you would elongate the whole depth budget. So for the most shots, you will stay close to the nearest object to not overemphasize the depth, because again, if you're putting the titles too much in front of the screen, you get rivalries there, because then you get occlusions and all that stuff. So you keep it most of the time close to that object, and in certain cases you have to decide if it's really behind the screen to put it also behind the screen or in front of the screen. So there is no sum of rule, but the only sum of rule is that you have to manually make them today.
Character moves, towards.
Yeah, when the character moves in front of the screen, a lot of people just shift the images to go in front. What we tend to do, because when you put them in front and they don't get bigger, this seems strange. Because normally, if the titles would come in front of the screen, they should also grow because on the retinal image. So what we do when we animate subtitles in the depths, we also animate the size, so that you really get the idea of that they are traveling with the audience.
So they're still traveling.
They're still traveling, yeah. Accommodation and versions. I just want to introduce it to you because this affects as well when you judge stereoscopic images on a small image. This will affect your depth perception on set, and you have to be aware of this to compensate for this and to see better, or to get a better understanding why when you watch something on a TV or on a small screen it does not look the same like on the big screen. We already know that the version's position is completely different, but this is another thing. Accommodation and versions. In normal vision, when we watch one object, we converge to that object, so we have a muscle effort for the convergence, and then we need another muscle effort to change the refraction of the eye, so like focusing. So you have two muscles that work together. So if you look in the distance, you relax the muscles, you look parallel, and you focus also in the background. And if you look at an object that is really close, your vergence muscle effort is going here, and then you get a trigger. Please also use the muscle for sharpness to put the focus here. And these are linked together when you watch here and here. So this is a reciprocal interaction of both muscles and fibers. But when we watch a stereoscopic image, whether it's cinema or it's TV, the focus, the refraction of the eye is always on the screen, and the vergence position is depending on the content. So we got a decoupling of those two muscle efforts. So things we have learned over 20, 30 years, always to have them coupled, are decoupled when we watch stereoscopic images. Yeah, it is learned and it is not inherited. Again, it's learnable. The problem is the blur. For example, we have an object on the screen and also the parallax is on the screen, then everything is fine. Then if an object is in front of the screen, our eyes start to converge on them, and then telling the muscles for the refraction, please move your focus point in front. They start to move the focus point in front, and they get the screen unsharp, and so everything is unsharp. Also the point in front, because it's just a stimulus caused by the screen. So our brain gets a conflict, because the screen surface gets unsharp. This is the problem of blur.
Never happened to me.
Yeah. I tell you why. To better understand this, I have to introduce you into the term diopter. Diopter is the unit of the diffraction of a lens. It's actually the reciprocal to the focal length, so 1 divided by the focal length. And the good thing about diopter is a same amount of diopter change is the same amount of muscle effort. So for each diopter change, we need the same change for the muscle effort. And as you see here, the same diopter is, in terms of meter, it's not linear. So these steps here are equal in diopter, but are not equal in meter. You can get an idea if you have a lens on a camera, the most movement is in the first meters, and between 5 and infinity, there is nothing anymore. And the same is with our eyeballs. So you have a lot of space here, and at the close distance, you have a lot of muscle effort. The Boeing Design Handbook, so from flying airplanes, have found out that a mismatch of plus and minus 0.5 diopters is still acceptable and comfortable. So we can easily calculate the limits of this mismatch of accommodation inversions by having the nearest point 0.5 diopters before the screen and 0.5 diopters behind the screen. But what does this mean? I have, sorry, this slide is in German, I haven't switched it to English. What does this mean? It means, for example, if you have a screen at 2 diopter, then the farthest point can be 1.5 diopter and the nearest point can be 2.5 diopter, always plus minus 0.5. Converted to meter, it's say, the screen is 0.5 meters away and your farthest object is 0.667 and the nearest is 0.4 meters. If you go to a screen which is 1 diopter away, you get 0.5 diopter for the far point and 1.5 diopter for the near point, and here you got in meters 1 meter, 2 meter and 0.6 meters. And if you go to a screen which is 2 meters away, you are at 0.5 diopter, and then the farthest point can be at infinity and the nearest point can be at 1 meter. So this conflict of accommodation inversions is affected by the distance to the screen. This is actually the same graph. Actually, you have this diopter versus meters, and you have always the same amount of plus and minus 5 diopters. And here you got this latitude. And if you are at 2 meters away, you can actually see that you can go to infinity and beyond, and to also really close objects. Marty Banks, and the other slides were from John Merritt, which is an excellent visual scientist, and I borrowed this one from Simon Watts and Marty Banks. They have put some smaller amount of allowable mismatch, and I found these values for television, which is more than 2 meters away. Or let's start with cinema. For cinema, the range, the cinema screen is so far away that your eyes are focusing at infinity and there is no effect by this cause. So there's nothing, so this accommodation inversions conflict is actually, yeah, it's not important for cinema. But if you reduce the screen size, and for television it's kindly relaxed, but this also limits your, also on the TV it limits your depth budget. So also you could achieve more disparity in terms of getting the limits of divergence. This kind of limit comes before. And then when you go to computers, computer games in stereo and smaller screen sizes, or tablet devices or cell phones where you have them really close, you see that accommodation and inversions can really make a big difference and can really limit the freedom of your stereoscopic imagery. So this can be a limiting factor. And now the last point, and then I think I made it in good time. I want to give you a short introduction in Gestalt theory applied to stereoscopic depth perception. And I'm not a psychologist and I'm not really into it, but it helped me for my work a lot to know a little bit about Gestalt theory. And I want to introduce you to the basic concept of Gestalt theory and how they may affect stereoscopic composition and also stereoscopic, for example, editing, because there it's pretty important. You can say that the visual system works in an analytical domain. So you get informations in your eyes and your brain processes all the information and reconstruct the picture. But this the Gestalt theorists say this is not true. It is true that you process the first bits of information and then you make an early decision of the image, how it will look like. And after that, all the other information, he tries to accommodate, the brain tries to accommodate all the later incoming information to fit into the image. So there is the bottom to top versus the top to down process. Bottom top, I told you, this is the idea of that the brain simply analyzes information units and reconstructs the image in the brain. But obviously there is something else there. It's not only a passive process, but also an active process. We always try to put parts, we try to order parts to give it one meaningful shape, one meaningful form. It's in German a Gestalt. And for example, this image and this image has exactly the same shapes, but we give it suddenly the meaning of a bicycle. It's the interpretation of the income information regarding to the earlier information. And this is pretty important when you want to make decisions, for example, in editing. I come to an example for that. Yeah, this is basically the same, the ordering in part. So the vision is a creative process. I give you an example. For example, if you have a wide shot with a really big interaction distance of your camera, and as we all know, if you have a really big interaction distance, your room gets miniaturized. Yeah? So you have one shot with a miniaturized scene and another shot where you have a smaller interaction of the same scene and the shot is not miniaturized. If you first cut the one with the big interaction, the brain makes the picture of the first information it gets, and it will make the image in mind, or the reconstruction. Oh, this is a miniaturized room. And when you then cut to the scene with the smaller interaction, the brain does not say, oh, the room is changing, but it will not exactly evaluate the picture because it wants to put the information to accommodate with the earlier perception. If you now change those two shots, show the audience first the one with the smaller interaction, and the audience make the image of the room with a really big room, and if you then cut to the one with the bigger interaction, the miniaturized room, you will notice that the room is not perceived miniaturized. So you can avoid miniaturization, or you can hide miniaturization in editing, taking into account the Gestalt theory. You can try this. This is it works. Who really was famous for this is Alain Deleuze, who unfortunately died 1 month ago. He was clever in doing his interaction and trying to hide miniaturization. And if you watch some of his movies and you stop at one frame and watch it for 10 seconds, you will see that it's completely miniaturized. But in the editing and in the fashion it was arranged, it will not be perceived miniaturized. Another example, all of my students, when I'm doing workshops with students, the first thing they want to do is the so-called stereo vertigo effect. So you have two cameras at zero interaction distance and then slowly move the interaction out. And what they believe to see is that the room is constantly growing and growing and growing. This is what they think they do, but if we know Gestalt theory, the brain sees the 2D image and makes a flat representation of the scene. In normal vision, we don't see rooms that deflate over time. So what will happen? You will see the flat image, and then when you change the interaction, the brain gets information that do not fit to his earlier image, and it will fight against them until the point he cannot negate the informations anymore, and then he will suddenly switch into a 3D representation. And in terms of feeling, it feels like you're having a 2D image, and then it opens and you say, this looks strange, and then pop, then it's suddenly 3D. So this is, if you take Gestalt theory for this into account. I have a stereoscopic Gestalt theory example, the last one. So what I'm showing you are four circles, just 4 circles with some corners in there, but you will all probably perceive, and I think it's flipped in the right way, perceive a white square floating in front of the background. Is this true?
Yes.
Yeah. So there is no white surface there. There are just 4 points. We perceive them. Our Gestalt theory tries to find a meaningful situation. And if I'm now just flipping both images, I have done nothing than showing you the left eye on the right image and the right eye on the left image, and the perceived situation is completely different. Now you will perceive 4 holes and the white paper lying behind the holes on a black surface. So or you can flip the glasses and you can see how the perception changed.
Go back to the previous.
So you can change the glass, it's the same, but I can go also back. So sorry. So I keep it, and you just move your eyes in the one and in the other, and you see how it's exactly the same image and how the perception
Can you
changes.
switch now?
Yeah, I can switch, of course. So this is the one, and this is the other.
Okay, back.
So Gestalt theory works in stereo 3D. I want just to show you this with this example. So I think that's it for me. Yeah, so I think here should be the 2 examples I've told you. The last thing is figure ground. The brain always tries to find an object which is the foreground of a picture, and it calls the figure, and everything else is the background. And you can not concentrate on both at the same time, to the foreground and the background. It's the winner-take-it-all strategy. And as this is my last slide, and this is my best slide because I'm at the end of my speech for now. And yeah, if you have any questions, I'm here.
I have a question.
Yeah.
Why with the last 2-dimensional pictures, we do have that victory where I was able to see just the man, and I was able to ignore the ladies. I don't know,
Yeah, so,
coddling
but you
the
cannot
babies
see
or
it
something.
both at the same time. This is what you cannot see the lady and the man at the same time.
Okay, but in the other situation, I was able to see both lines at the same time, right? They would be battling constantly back and forth.
Yeah, this is a little bit different, but rivalry and Gestalt theory is a little bit a different domain.
Okay.
So don't mix them up.
Okay. So it's just
Yeah.
because of that.
This is a cognitive process. This is cognitive, so we use our brain, our experience, everything. The rivalry is really neuronal fightings. There are neurons shooting information to the brain, and this is
So one
cognitive.
is learned. Okay.
Yeah.
Great. Thank you.
You're welcome. Any other questions? I think we have a party now. Or barbecue.
Starting first, start later.
Okay, I have a question.
Yeah.
How about the occlusion of surfaces or objects like a glass? So they are
Transparent.
and
Yeah.
reflect and
Yeah.
reflect
Yeah.
and refract.
Really
the
good
light.
question. Really good question.
So I noticed that the bigger interaction you have, the stranger the objects looks in the screen.
Yeah. Volume perception is really beyond the scope, and the surface perception is really not surface perception, volume perception, how we perceive volume and how can we figure out which pixel or which cells belong to which object. This this is really where we have to have the most effort in fusioning the images. This is where, when we get semi-transparent objects, smoke, all that stuff, this is why it looks so really good and amazing, because when we watch something semi-transparent, our neurons in our brain, they really fight, and it's really a really complex decoupling, and this is why it also gives you this exciting feeling. So semi-transparent objects are hard to handle in post, because you cannot do all the stuff you have to do. But transparent objects normally are really giving you a really rich stereoscopic image. Because you notice that the left and the right image are not really similar, and of course if you stay in the limits, this volume can add, can materialize the room. If you have an empty room, you got no 3D, but if you have volume in the room, volume that you see, you materialize the volume, and therefore volume perception is also one of my research topics. How do we perceive volume, and how there is a correspondence problem, because you cannot match one eye to the other, because you have different depths that are mixed together, and they are mixed together in the left eye differently than to the right eye, but we can figure out it in somehow. And there is a lot of research going on, and also in the past, also in the 70s, but completely understandable it's not. It was not the answer to your question, but
yeah.
Okay.
But in real life, we also
we have volume.
The
yeah.
same.
Yeah, we have the same. Yeah, and for a lot of stereoscopic pictures, volume, smoke, haze works really good, because it materializes the image, and it gives you this additional correspondence problem which you have to solve. And this is activation. This is activity in your brain, and this activity gives you this excitement, this add-on. This is a real add-on to 2D volume, transparency.
Thank you very much.
Thank you.